Good morning, Internet. I am Matt Buyak. I hope your weekend's going well. In this video, I'll be taking a look at the 43rd problem from the Project Euler problem archive. This problem asks us to consider 10-digit pandigital numbers, that is, those with the digits 0 through 9 exactly once each, that have this peculiar divisibility property. And then our final answer will be the sum of all such numbers. Now, this divisibility requirement here is a little bit odd, but essentially we need to take the k plus first, k plus second, k plus third digits from our number and form a 3-digit number. And our goal is that for any value of k, the result will be divisible by the kth prime. That is, if we take the second, third, and fourth digits, for example, then the number that results should be divisible by 2, the first prime. Now, we did a similar problem to this a few days ago on the channel, this problem here, which dealt with pandigital numbers that were also prime. And in order to solve that problem, we used this function, next permutation, to permute the digits 1 through 9, looking for pandigital numbers that were also prime. And we could take the same exact approach with our problem, but keep in mind that the number of permutations of elements of a set is equal to the size of that set factorial. And so permuting the digits 0 through 9 instead of the digits 1 through 9, as we were in this problem, is going to take 10 times as long. And fortunately, today's hardware is quite capable, so that might not be much of an issue. But if we look at the published date for this problem, you'll see it was just about 20 years ago. I was a college freshman at the time, and the hardware back then was a little bit less capable. Now, I will say that there is no time requirement on Project Euler. That is, there are some coding contests and coding puzzle sites where your problem or your solution must finish in under a certain period of time. But Project Euler has no such requirement. So 20 years ago, we might have left our solution running for 30 seconds or a minute until we got our answer. But we can be a little bit more clever than that. And the key to the trick that we're going to use is to consider what happens if the fourth digit, just to give one example, is odd. Well, the resulting 3-digit number, when we take the second, third, and fourth digits, would also be odd. And so that means it wouldn't be divisible by 2. But using our next permutation function, our algorithm would happily continue permuting the digits 5 through 10, looking for possible solutions, even though once we've put an odd digit in the fourth position, we already know that we don't have a solution. And so we waste a lot of time considering possibilities that just aren't going to be solutions to our problem. And so the way we're going to solve this is to build our number 1 digit at a time, making sure that at each step our candidate solution meets all the divisibility requirements. Now, one final note before we get into writing some code. It would technically be more efficient to build our number right to left rather than left to right. And that's just because the divisibility checks for the right end of our number are more restrictive. And anytime you have some sort of exponential search, it's good to eliminate as many possibilities as early as possible. And there are fewer numbers which are divisible by 11, 13, or 17 as compared to 2, 3, or 5. However, it is a bit more awkward to build our number right to left than left to right. And it's not that much more efficient. And so I'm going to start left to right instead, even though it's not quite optimal. And with all that in mind, let's get to writing some code. As usual, I'll copy our template directory to make our problem directory. And go into our problem directory and open our main.cpp. Okay, so the approach that I'm going to take to building our solution one digit at a time is going to be a recursive function. So basically, our function is going to consider all of the digits that we haven't used yet, and is going to try each one in turn. And then the function is going to call itself to deal with the remaining digits that need to be added. So let's see how that works. We'll call this maybe, we're going to need to return an integer. But actually, a regular integer is not going to be quite sufficient. We're going to be adding up a bunch of 10-digit numbers. And so it's pretty likely that we're going to exceed the size of a standard integer. A standard signed integer can hold numbers up to roughly 2 billion, and an unsigned integer roughly up to 4 billion. But adding up a bunch of 10-digit numbers, it's quite likely we'll exceed that. So we actually need to use an int 64t. And we'll say solve recursive. And we're going to take our number in progress. So we'll say int 64t candidate. And then we need to keep track of which digits we have used. And so I'll use a bit set with 10 elements. A bit set is just a, you can think of it as an array of bits, but it's stored more efficiently depending on the implementation, than actually using an array of bools, for example. That's because a Boolean usually still uses at least a full byte. Bit set is likely packed into individual bits. So we'll say used. So these are going to be the digits that have already been used. And we can actually make this a default argument. So we'll say std bit set. Oh, I suspect that you can't see this. That's unfortunate. Well, I'll just so that you can see it for a moment. My editor is not cooperating. There we go. So this is what this line looks like. I'm going to put it back up on the... I suspect the webcam is blocking this, but sorry about that. Okay. So now the first thing that a recursive function often needs to do is check to see if we're in the terminal case. That is, if we've added all of the numbers that we need, or all of the digits that we need to add, then we can return some result. So let's do int count is going to be equal to used.count. So we're going to check how many digits we've used thus far. And we'll say if count is equal to 10, then we'll just say return candidate. Okay, but if we haven't added all 10 digits, then we'll want to consider each of the digits that we haven't used and try adding those to our number. So let's say for int I is 0, I less than 10, increment I. And we'll say if used.test I, then continue. So this is just saying If we've already used that digit, don't consider it. Go on to the next digit. Okay, so at this point, we know that we have our digit that we're going to try adding. So let's say candidate times equals 10. Actually, let's do it this way. We'll just say candidate equals 10 times candidate plus I. So that's going to, multiplying by 10 is basically the same as adding a 0 to the right-hand side of our number, and then we can just add our digit to get our new candidate. Okay, and so now we'll want to do our divisibility check, and let's just make a little an array up here. We'll say std array. It's going to be an array of, was it 7? Yes, 7 divisors. So we have the first 7 primes. We'll call it divisors. And it's going to be 2, 3, 5, 7, 11, 13, and 17. Okay. Now, if our we have to be a little bit careful looking at going back to the problem statement for a moment. You'll notice that we don't actually do any divisibility checks with the first, second, and third digits. And so if our number has fewer than 4 digits, then we don't need to do any divisibility check. So let's say, now we have to be a little bit careful here because count is actually the number of digits that we had before we added our most recent digit. And so if our number had 3 digits previously, it will now have 4 digits, which means we can do divisibility checks. So we'll say if count is less than 3, so if it has exactly 3, we will do divisibility checks. If it has fewer than that, then we won't. So we'll say if count is less than 3, or, and now we need to do our divisibility check. And so the way we'll do that is to take our candidate number mod 1000. That gives us the 3 rightmost digits. So we'll say candidate mod 1000. And then we want to take that, mod our divisor. So divisors. And we have to, again, be a little bit careful about how we select our divisor. If count is equal to 3, that's the first case in which we'll be doing division checks, and we'll use the first divisor, which is 2. And so we want to do count minus 3 to get our divisor. And if our candidate mod 1000 mod our divisor is equal to 0, that is the division, or it divided it evenly, then our candidate is still good. We can consider adding more digits to it. Oh, we need to keep track of our solution, obviously. So let's do int 64t solution starting at 0. And then we'll say solution plus equals, and now we will recurse. So we'll say solve recursive, and we pass it our updated candidate. Oh, we also need to be careful to update our bit set. So let's say used dot set I. So we're indicating that we have used the digit I. So then we'll pass our candidate and our bit set, and update our total number of, or the sum across our solutions. Okay. Now, this is a common mistake that I remember making many times when I was first learning about recursive functions and such. It's important that if you modify your state like this, that when you return, you undo the changes that you made. In particular, we don't want to, if we don't remove the digit that we just added, as we continue to iterate over more digits, we'll just add more and more digits, which is not what we want. So we want to be careful to say use.reset I and candidate divide equals 10. So that's just going to remove the digit that we just added so that we can try adding a different digit instead. Okay, and then once we've tried adding all of the digits, we can say return solution. And then in our main function, we should just be able to say printf solution equals %long unsigned solve recursive. And we're starting off with our candidate as, actually, we can make that also a default argument. I made our bit set default to an empty bit set. We can also make our candidate default to 0. Okay, I think that should be good. No, there's a few includes that I've forgotten, as is often the case. So let's say include array and include bit set. And I think that should be good. We have a minor mistake. Yes. You might not even be able to see this. Let me add just some blank lines there so you can see what I'm doing. I missed the template argument here, so we need that to be 10 to indicate that our bit set has 10 bits. Let's go back here, build, solve, and we get our solution. You'll note that if you count the number of digits here, roughly 16 billion, definitely exceeds the size of a standard integer. So we were right to use 64-bit integer. So now let's go back to the archive. And we can scroll down to our problem. As is often the case, it appears to have signed me out of Project Euler. I think they must have changed something at some point. These days, it seems to be particularly aggressive about signing you out. Just in the space of the time it takes me to solve one of these problems, it tends to kick me out. OK, so let's try again. Going down to the 43rd problem. And we see that that does, in fact, match our answer. So as always, thank you very much for choosing to spend some time with me today. And in the next video, we'll be solving problem number 44. I hope you'll join me.